All right, let's dive into something really cool from computer science that's all about strategic teamwork. It's called Alternating Time Temporal Logic, or ATL for short.
Okay, to really get this, let's start with a great analogy. Imagine you're trying to describe the future. Most logics out there? They're kind of like weather forecasters. They can describe the weather, a single possible series of events, or they can describe the climate, which is just all the possible weather patterns that could happen. But ATL is totally different. It's like having a team that can actually seed the clouds and guarantee it's going to rain. See the difference? It's not about what might happen. It's about what a specific team can force to happen.
So this powerful idea is really the heart and soul of ATL. It was formally introduced back in 2002 as a way to specify and check on systems that have a bunch of different autonomous agents all doing their own thing.
Right, so here's the kicker. ATL basically says, let's treat everything like a game, a strategic game. This lets us formally reason about stuff like strategy and cooperation and whether a team can actually win no matter what its opponents or the environment throws at them. So how does ATL actually do this? How does it express this idea of team power? Well, it has this unique tool called the strategic quantifier. You can think of it as the special grammar the logic uses. Instead of just describing what might be true, this thing lets us ask, does this team have a winning plan?
And that leads us right to this core concept, coalitional ability. Now, it sounds super formal, but all it really means is that a team has a winning strategy. It's not about just hoping for the best outcome. It's about having a concrete, solid plan to force the result you want.
Yeah, and this slide just illustrates the whole thing perfectly. Forget all the complex symbols for a second. At its heart, an ATL formula is just saying this simple sentence. It lets us ask really specific questions, like, does this group of robots have a collective plan to guarantee they all dock safely?
So let's break this down, because it's super important. First, you need your team. That's the coalition. Then, you've got your goal, like reaching a certain place. Next, you need a winning strategy, which is a complete playbook for every single member of the team. And, this is the crucial part, that strategy has to be bulletproof. It has to work no matter what the environment or any opponents decide to do.
But wait, there's more. ATL isn't just one single logic. It's more like the foundation for a whole family of logics, each designed for even more complex, real-world situations.
We've got some really important extensions here. There's ATL, which brings in what agents actually know. I mean, think about it. Can two robots really coordinate if they don't know each other's location? Then you have RBATL, which is huge for systems with limited resources. It helps prove a delivery drone has enough battery to finish its mission. And there's even HyperATL, which can tackle these thorny security questions, like proving a system can stop information leaks and keep your data safe.
Okay, I know this might all sound a bit academic, but this is where it gets really cool, because ATL has some massive real-world applications. This is why it all matters.
It's used to verify that teams of robots or software agents, we're talking fleets of delivery drones, can actually work together to get a mission done. It's about ensuring your package arrives on time, even if some of those drones face unexpected problems along the way.
And it's not just about checking systems that already exist. It's also a game changer in AI planning. In this case, we don't just ask if a system can succeed. We use the logic to actually build the winning strategy for them. We're literally writing their playbook.
And get this, it's even used to design social rules for AI. Think about autonomous cars on a highway or service robots in a hospital. We need to make sure they interact in predictable, safe ways to avoid total chaos and make our lives fundamentally safer.
And here's something that might surprise you. For a lot of standard cases, verifying a system with ATL is incredibly efficient. The process runs in what's called linear time. In the world of computer science, that is a huge deal. It means we can actually apply this powerful logic to big, messy, real-world problems. So, let's bring it all home. What's the big takeaway from all this? Well, ATL represents a pretty fundamental shift in how we think about autonomous systems.
It gives us the tools to go beyond just wondering what might happen in a complex system. It lets us mathematically prove what a coordinated team is capable of achieving. Guaranteed. And that leaves us with a really fascinating question for the future, doesn't it? As our world fills up with collaborating AIs, from self-driving cars to automated warehouses, how are we going to write the rules that guarantee they succeed together?